Somebody confirms that my screen is visible.
Yes, sir, it's visible.
Yes, sir, it's visible.
Great. So we were discussing about a few very interesting aspects of, like, first is force is equal to mass into acceleration. How that is connected to, see the Navier-Stokes equation, that is rho dv by dt is equal to minus gradient of P plus mu del square V plus rho g. Okay. In that regard, you have come to know that it's a direct consequence of that. And then we were discussing about, while doing so, how exactly this P originates, and then how exactly you correlate the stress to two properties, two different properties. For solids, how you correlate. This is for liquid, how you correlate to the strain rate. And then for solids, how do you correlate to the strain? So today we finish this part. Last class we discussed about the strain rate part. So today we finish the strain part to make sure that the entire story becomes complete. So in that, for solids, we decided that say capital X is the original configuration or reference configuration. Small x is the deformed configuration or the final configuration. And based on that, we develop different types of, say suppose if x is the position vector that is in the deformed configuration, and capital X is it is expressed in terms of capital X. You can write the position vector like this at a particular time, and from there you can define the velocity and the acceleration. So the calculation of all the forces will happen within this framework, and this we called as the Lagrangian description. Whereas you can also do the same analysis by expressing everything in the final configuration, and that description is called the Eulerian description. So this we are more or less comfortable with. Now, when I'm writing the Navier-Stokes equations, you may think that this is all in the deformed configuration I'm writing, right? Whereas you can also write the same thing in the reference configuration. When you are going for the fluid, we all do everything. We do everything in the Eulerian configuration. Whereas when I'm talking about solids, you will find we will restrict our things towards the reference or the original configuration, because solids, they deform less, they move. When you have a projectile motion, there is no deformation, right? So it is obvious that it is very easy to start, calculate everything with respect to the situation which is time t equal to 0. But for fluid, there is nothing called initial. So it becomes very difficult to go back to anything which is at the initial configuration. So that's the reason why we do the fluid calculations in the Eulerian domain. And then, we define the same thing, and we saw this, that, that anything is consequence for any type of deformation or any type of motion is a consequence of what? Deformation plus rotation, displacement plus rotation. This we have discussed in multiple number of classes. And then, we defined a motion u, which is small x minus capital X. Initially, it was capital X, then it has become small x. And from there, we define the deformation tensor F, which is basically a transformation matrix. So dx, if you want to convert anything related to dx, that is F capital dx, right? So F dot capital dx, if you have a transformation a matrix F, which looks like this, if you take a dot product with dx, you are going to get dx. So this F is called the deformation tensor. Similarly, it can also be written at dx dot F transpose. So not only dx can be dx can be written in terms of d small x, can be written in terms of d capital X, but also D capital X can also be written in terms of D small x. So these two formalisms are all interchangeable. You can interchange with each other. So F essentially you write dx, D small x by D capital X transpose. This is what is your F. Whereas F inverse transpose is D capital X by D small x. Okay, which is something like this. Now, what is the utility of this? We understood that Jacobian of this deformation matrix, if it remains to be 1, then it's an incompressible material. This is straight away coming from the kinematics, whereas the Jacobian, if is not equal to 1, that means there is a degree of compressibility associated with the system. Now look at how exactly Hooke's law is emerging from here, from this simple argument, how the Hooke's law is emerging. Okay, so now instead of having dx, only dx, you think about dx dot dx. It's like, something like an area you are thinking about now. Dx dot dx, which you call as a ds square, which is the area, right? And d small s square is the area final, which is maybe this, and d capital X square is the initial area. So if you just place all of them, so suppose d small s square is dx dx. Now dx, you know that dx dot f transpose dot f dot dx. Okay, so if you write like that, so if transpose into f, you express in terms of c. This c is called the Cauchy-Green, right Cauchy-Green deformation tensor. If you write the other way around, this is the left Cauchy-Green deformation tensor. So these are also again interchangeable with each other. Now, what is the consequence of that? Now, if you take ds square minus ds square, right, then you get what? 2 into dx into e into dx, which comes in the middle, between these two, this e. Now this e, if you expand, it comes out to be something like this. Okay, where e is half of ft minus f minus I, that is half of c minus I. Right, now if you expand it, you will find that, say what is this particular term? If I write E11, what is this? This is nothing but, you see that this is equivalent to what? This is equivalent to say del u by del x. This is equivalent to y, del v by del y. Here I am talking about u, v, w, all are displacements. Okay. So here I am talking about a displacement matrix. It can also be extended to the velocity matrix. But then you see that these three terms are essentially u1 means x directional displacement divided by x1. This is y directional. Of course, this is all capital because I'm talking about the initial configuration or the reference configuration. This is del w by del y, del z, right? Now what are these terms? These are nothing but half of del u by del y plus del v by del x. So you can see that terms which are very similar to the cross terms del v by del x. So similarly, the cross terms, if you take this, and this, you will see that you are going to get the cross terms. What are those cross terms? We have already shown. Like say, suppose you can see that this diagonal, and at the same time, so these are the normal stresses and these are the tangential stresses. So you may see that the normal stresses and the tangential stresses, they appear very easily from the geometric argument only. Whereas when you have taken a motion like this is that final area, this is the initial area. There's a motion that has taken place. Now, if you summarize everything, you see that there are additional terms coming in. There are additional terms coming in like this, like this, like this, like this. Can anybody tell me what are these terms? What is happening here? Why this discrepancy is coming up here? Anybody has any idea?
So we are combining the effect of one direction on the other direction. So it's
So until now, we were assuming that, if I write here, okay, until now we were assuming that sigma ij is what is proportional to what gradient of u plus gradient of u transpose, right? This is we're assuming. So now if you look at this epsilon eij, so this is essentially the sigma ij I'm writing is proportional to epsilon ij, right? Now epsilon ij is a representation of that. Now if you look at this you can think about this is the gradient of u, and this you can think about this is plus gradient of u transpose, right? And then you have this additional term coming in here, which is the consequence. These are the terms which is summarized like this. Now, why this particular term is coming? What is the reason? When I am looking at a very generic motion, which is this, which was dx in the beginning, and then it had d capital X in the beginning, and it has become d small x at the end. Now, if I really go for a kind of like two-dimensional, three-dimensional analysis, I will see that there are terminologies coming in, but up to this point we have considered everything is like this. Everything is like this. Now, why am I getting these terms? What is the answer to the question?
sir, in the Taylor series expansion, we are not ignoring the lower or the second order terms. That's why I guess, like in the earlier cases.
What was the assumption we had in case of in case of solid liquid? What was the main assumption that we had? See, when we went for this, where is that?
A small displacement, like the chain was a small.
Yeah, so we always were considering here that this is the assumption that we were enforcing, that this is a small deformation problem, right? Since we were considering this to be small deformation, we could get away with this because this we did not really consider. Actually, theta 1 plus theta 2 is not this, but if you take all the geometrical arguments together, then theta 1 plus theta 2 will be something like this. And this is actually, so green strain tensor is the most generic strain tensor, which actually considers all the deformation. Whenever you are extending, whenever you are shearing, whenever you are deforming, you have all the strains that are integrated to this. So this actually has all the terms that are necessary for the to describe any deformation, small to large. Now, in case of Hooke's law, in case of Newton's law, we get away with this thing, assuming that this is a small deformation problem. Okay. Now, these terms are called the nonlinear. You will find all these terms have a nonlinearity associated with that, which is again called the geometric nonlinearity of the system. So if there is a phenomena which has a lot of nonlinear dynamics, so you see that gradient of u transpose, also have a dot product between the gradient of u and gradient of u transpose, which generally we ignore. That term you cannot neglect for a problem where if you have loaded it in such a manner, there is a large deformation associated with that. Okay. But then, you can get away with the small deformation problem, and green strain tensor looks like this. Okay. And then this is the rotation tensor, and that E and sigma you add, then, you get the total rotation associated with that, which is the basis of the Hooke's law. Now you see how Hooke's is, weaving his argument in order to really cook up the Hooke's law. So what he's suggesting in the beginning that the stress is a function of this deformation tensor, that is F. He's saying that stress is a function of F. And then he's saying that, this sigma is equal to what? Del U0 by del epsilon, where U0 is the strain energy density. What is that? You have an object and you have put some stress into it, right? What is the stress? What is that object? Object is having a lot of sigma bond, pi bond. Say suppose you have a sodium chloride lattice. So it has an ionic bond structure, FCC. Now on that, when you are pressing it, when you are putting up a stress, you are basically stressing those bonds. Now those bonds actually are going to resist your stress or pressure that you are trying to put. So what first assumption or first insight into the whole thing that says that whenever you put sigma, that sigma is going to act on what? That sigma is nothing but the strain energy. It is going to really work on the strain energy. Even if it is deforming, it is able to really bend that bond or compress that bond, right? So what is energy? Energy typically, what is the unit of energy? What is the unit of energy? You say that this is joule, right? That means this is Newton meter, right? So energy density means joule per meter cube, right? So Newton meter per meter cube. That means this is Newton per meter square. What is stress?
Newton per meter square.
Stress is also Newton per meter square. So stress can be expressed as the strain energy density. A material is said to be hyperelastic or green elastic if there exists a strain energy density where sigma is what? Del U0 by del epsilon. So essentially you write sigma ij equal to del U0 by while U0 is a scalar and epsilon ij and sigma ij are the different types of stresses. So you have an object around which you are applying a lot of things, right? So when you are pressing it, the energy, you are overcoming the energy to cause some strain. That's what is expressed here. Now for an incompressible elastic material, sigma is nothing but you take the principal stress out or the normal stresses out, and then you keep the deviator part here, which is del U0 by del epsilon. This we have already argued in a big way. Then what you do? You say that this particular term, U0, you expand about epsilon 0. That means initially there is no deformation, and then as the deformation takes place, that is with respect to epsilon ij. So with respect to U0 is expanded with a series about epsilon equal to 0, which is obvious. Epsilon 0 means undeformed configuration, and when simultaneously epsilons are coming, then this is becoming slowly deformed. So if you do a Taylor series with respect to epsilon 0 ij, it will look like this. Now you take a few terms there, especially first 3 terms you take. Then what you do? You make a derivative, sigma mn, okay, is equal to del U0 by epsilon mn, and then you get these terms. Now in that, if you do a little bit of rearrangement, what you get finally, you get Cmn into Cmn ij epsilon ij. So if you are doing a Taylor series expansion with respect to sigma mn, you will finally get Cmn plus Cmn ij epsilon ij. Okay, this is the most general form of the Hooke's law, where the Cmn is associated with what? The Cmn is associated with the term called residual stress. What is a residual stress? The stress that is already built inside the material. When it is C0, everything is under stress condition, right? Even at epsilon equal to 0, you have a stress that is inside. So Cmn is a representation of that. Now, if you cause a deformation, okay, or strain, which is expressed by epsilon ij, so generalized Hooke's law say that sigma mn equal to sigma mn is equal to Cmn ij epsilon ij. Okay, if you consider this residual stress to be 0. Now Mn, there are 9 components. Ij, there are 9 components. So how many components will be Cmn ij?
9 into 9, 80.
So there are 81 components. What is the Cmn ij? Anybody has any idea what is the CMNIJ?
4D tensor.
Tensor fine, but what is this? Stress is proportional to strain. You put a constant in the middle, right? In order to make sure that it's the equation. What is that? What is this? Then what is the constant that you get for stress is proportional to strain?
Viscosity in case of fluids.
Stress is proportional to strain for solids. What is the modulus in the
Young's modulus. Young's modulus.
Yes. So this is nothing but the most general form of the Young's modulus. So now why are you getting 81 Young's modulus? How are you getting 81 Young's modulus, by the way? So you can think about a three-dimensional axis system here. Okay, which is first converted into 9, right, like this. Okay. And then each one of them are converted into 3. So 9 for stress, and then each stress is associated with 3 more, right? So that is leading to your altogether how many? So now you can see, right? All total how many are there? So these are the different directions you have the modulus. That is the most generic possible material that is available. So you have that many modulus in a system. Okay, that is the most generic possible material. All the moduli are different. It's anisotropic, fully anisotropic material. Right? Then what you do, you start putting the symmetry arguments. So it is about 81 you have. However, the components Cij is satisfied. This is always by definition, it is always there. So which reduce the whole thing to 21. 81 to 21 straight away comes out from this symmetry arguments. What is a symmetry argument? Say suppose I take a material, right? I take any material. Say suppose I take this plastic, and then what I do, I start stressing from this side. I start stressing from this side. Now, question that I ask: if I put same amount of stress, will the extension be same? If they are same, that means stressing from this side, that side really doesn't matter. So the material is symmetric around that. But if they are not doing that within that material is anisotropic, and then you have to consider do 2 different modulus in 2 different directions. Right? So one puts various symmetry arguments on this Cij. So first is this symmetry argument. Then happens if you have a monoclinic material. Okay, if you have a monoclinic material, right? So when the elastic coefficients at a point have the same value for every pair coordinate systems, which are the mirror images of each other with respect to the plane. For example, let x1, x2, x3 and x1 star, x2 star, x3 star be 2 coordinate systems where x1 and x2 plane parallel to the plane of symmetry. Choosing x3 axis such as x3 is minus x3 star. Right? So in that sort of situation, you put some sort of symmetric argument like this, right? In order to really cancel a few coefficients, right? Leading to what? Leading to in 21, you get rid of 8 by considering the material to be a monoclinic material. What is this? What are they saying? That say suppose there are x, y, and z. Suppose x3 is z. So around z, I see that one side of the z and the other side of the z, whether they are mirror image to each other or not. If that is the case, then your another 8 coefficients are down. Similarly, if you put an orthotropic material argument, in the orthotropic material argument, you just have to have say 1, 1, minus 1, minus 1, 1, 1, 1, minus 1, 1. If you do that, then what happens? You will see that this becomes 9 plus 3, 12. Right? For an isotropic material, what happens? All these coefficients, they boil down to two major constants. One is called the elastic modulus, another is called this new, which is called the Poisson ratio. So if you put if you have a material which is exactly symmetric, which is also called the isotropic material, right? In that situation, you end up getting two constants. Both the constants are called the Lemay constant. One is the elastic modulus and the other is the Poisson ratio. So the stress is proportional to strain. You end up getting an equation which is called the Hooke's law of elasticity. Okay, you can also write the strain in terms of stress. This is the way it is written. Stress is in terms of strain. This is the way it is written. Strain in terms of stress, where this elastic modulus is the measure of how much difficult the material is to deform, whereas the Poisson's ratio is a measure of whether the material is compressible or incompressible. Okay, if the material is incompressible, then Poisson ratio is always 0.5. Right? If it is away from 0.5, then the material, because if you put nu equal to 0.5, you will find that this term will vanish, right? So and only you will get, like, for nu equal to 0.5, your stress will become what? Your stress will become only, like, this P will come. This is the only pressure term that will come. And if nu is not equal to 0.5, what is the consequence? If nu equal to 0.5, that means half, right? So this will become infinity. That means this term will become what? This term, you have to make sure that this EKK is 0, right? So you can see that there is a delta Ij term also, right? This delta Ij term, this term is associated with what? This term is associated with then the pressure. So in case of an incompressible material, in case of an incompressible material, what will happen? In order to make sure that, since this is becoming infinite, in order to be consistent with the algorithm, what will happen? EKK has to be 0, right? And that's where the origin of the pressure, the pressure origin is there when EKK tends to 0, and when nu tends to 0.5, the invariant that pressure that manifests, right? So this is the consequence of the pressure, and this is the consequence of what we generally get. What is that? This is 0.5 means what? You will get this epsilon, this E already is the elastic modulus, right? So you get what? Epsilon Ij, sigma Ij is proportional to epsilon Ij, right? So now, if this is the elastic modulus, if this is the Hooke's law, then if you plot sigma versus epsilon, what you get? You get a zone where this is linearly elastic. If you really have a kind of solid object, and then if you are pulling with a load, you are extending it. What will happen? Up to a certain point, if you stretch it just like a spring, if you take a spring, if you stretch it up to a certain point, what will happen? It will come back to its original shape. Whereas if you stretch it beyond the limit, what will happen? It will not be able to come back. So in that sense, what will happen? It will become non-linearly elastic. And the transition point from the linear to non-linear is the point that is what is the point beyond which, like, this is not linear, right? And then after that, beyond a certain point, it will show, like, a very abnormal behavior, before which, like, it is just going to fail. And that particular point is called the yield point. Now, until the linear domain, what will happen? Until the linear domain, what will happen? It will not show until this elastic limit. It will not show, like, any hysteresis. If you just unload up to this point, what will happen? It will come back following this way. There is no hysteresis. But if beyond the elastic point, if you go, what will happen? It will show some sort of hysteresis. It will not come back the same path that you have loaded. And beyond yield point, there will be a failure of the material, like, beyond which, you just cannot have any elastic property that is remaining. So what is the representation of a Hookean solid? It is the spring. What is the representation of a viscous fluid? It is the dashpot. Typically, people consider that. Say, suppose if you have a spring like this, so then, and then, you are loading on top of that. This is a kind of elastic material. And if you have a dashpot like this, so dashpot means you have a piston and you have a water filled jar and you are pressing the piston. So that is a kind of signature of a viscous fluid. Now here, once you press, what will happen? The liquid will flow up and then liquid will just cover. So this piston will never go back. But here what will happen if you load, this is going to compress, this is going to compress. And then if you unload, it is going to expand. Right. So there is a sort of, in this sort of elastic material, you have a sort of memory. The solid remembers its shape. So when you press it, it is going out of shape. It is getting deformed. When you unload it, it is getting back its shape. So it remembers its shape, and that is represented by a spring. Whereas in case of a liquid, when you press it, it rearranges it in such a manner so that it just dissipates the energy, whatever energy you are putting in. And in that situation, what happens? It forgets its memory. So this E also is called the storage modulus. Larger is E, larger is the storage, whereas this mu, viscosity, is called the loss modulus, because higher is mu, that means higher is the energy. In a fluid, whatever energy you invest, that is lost. In a solid, whatever energy you invest, in a Hookean solid, whatever you invest, that is stored. Okay, so that actually creates the platform for you to analyze the materials which are not solid, not liquid, and which are called the viscoelastic materials. Until this point, it is clear. So this is the first origin of, this is the first proposition of a constitutive relation where stress is correlated with strain. Okay, stress is correlated with strain, right? And then, any type of correlation of stress to strain rate is called what? It is called the constitutive relation, right? So, what is that? You say that this stress is what? It's a function of the deformation. And from there, you weave the argument in order to really put the sigma. And in sigma, you see now, the formulation is given how exactly you take the pressure out. Now, this is the deviatoric part, and this is what? This is the pressure part. And this mu and lambda, these two are called, these two constants are called the Lames constants. Okay. Now, of course, sigma has a pressure term and the deviatoric term. This is for a fluid. And we have talked about the different types of fluids, like, say, suppose Herschel-Bulkley, Bingham plastic, like paste, power law, shear thickening, like, quicksand, Newtonian, which is like water, power law, shear thinning, like paint. So different types of constitutive relations are available. What these relationships are, see, by the way, these are not law. These are all different types of experiments performed. And from those experiments, people have summarized that, okay, this fluid behaves like this, that fluid behaves like that. So in that process, there are a number of classifications in terms of different types of fluids, especially in the biological domain, in microfluidics. These type of non-Newtonian phenomena, they emerge in a big way. Even water in carbon nanotube, it flows in a non-Newtonian manner rather than a Newtonian manner. Okay, so one need to really know different types of constitutive relations in order to tackle those problems, right? So if you for a fluid, you plot shear stress versus shear strain rate, and there you can really differentiate between shear thinning, shear thickening, Newtonian, Bingham plastic, and then what are the other types? Thixotropy and Liouville. This we have discussed in a great detail in the last class. And then we also argued at the molecular level what exactly is making it shear thinning while layer formation is taking place, and then cross-link arrangements leading to the shear thickening behavior. Right now, since we were talking about this, the elastic, the spring and the dashpot effect of the viscoelastic effects. So this is a very famous Weissenberg effect experiment that in general, if you rotate, if you take a glass of water and with a spoon, if you rotate the water, in general, if it is a Newtonian fluid, what will happen? You will develop a swirl which is going towards the bottom, right? So it will just go towards the flow. The way if you are rotating like this, like if you go to Brahmaputra river and see the swirl, so it will create a kind of conical funnel type situation. However, some fluids, if you just, rotate like this, these fluids will climb up like this. This is called the Weissenberg effect or rod climbing effect, right? Where, if you are having a Maxwell's fluid, which is rotating at a very high speed, what it will do, it will just, allow the fluid to climb, right? Now, this sort of fluids are called the viscoelastic fluid. So how exactly you design them? You design with the help of a spring and dashpot model, right? Say, suppose if you, instead of only having a spring, if you have dashpot on top of that, right? So, and then now load, what will happen? A part of energy will be stored and a part of energy will be dissipated. And that can be represented by tau plus lambda d tau by dt is equal to mu gradient of V transpose. This is another constitutive relation. Okay, where lambda is the unit is second, and this lambda is called the relaxation time. And this lambda is nothing but mu by E. Mu is what? Pascal second. E is what? Pascal. So mu by E is what? It is second. So lambda is second. This is the relaxation time. What is the meaning of this relaxation time? The relaxation time means, say, suppose in this sort of fluid, you have put a load, you have stressed it. Now, moment you release the stress, after what time it is going to get its original shape, this relaxation time is a measure of that. So mu is a measure of how much energy has been dissipated. E is a measure of how much energy has been stored. The ratio of mu by E is going to tell you how fast the material is going to get back its original shape. If it is infinite, then what is that? If the relaxation time is infinite, then what is that? If you have a material and if your relaxation time is infinite, what is that?
It's never coming back to its original state.
What is that material?
Inelastic.
It is a fluid, right? And if lambda is equal to 0, what is that material? That means it is going to come back to its original state immediately, correct? Immediately. Lambda is 0 means
Yes,
what?
sir.
So lambda 0 means it is going to come back to its original state immediately, just now. So that material is called what? That material is called the elastic material, right? So relaxation time actually gives you the idea of, like, how quickly you get back the material. What is the type of material? If lambda is finite, that means that material is a viscoelastic material. So essentially you have to deal with three parameters. One is the viscosity, the other is the elasticity, and third is the ratio of these two, which is called the relaxation time. Okay, so I think this is good enough. Most of the concepts related to, first, Hooke's law, second is the Newton's law, third is the laws of motion, fourth is the constitutive relation, and third is the different types of possible materials in the microfluidic devices. We have discussed up to this point. Okay, any question you have? Any question? No questions? No more questions? किसी को कोई सवाल नहीं है? सबको सभी समझ में आ रहा है? Interesting. Good. So 23rd, next Wednesday, we have the presentation. Am I correct? All of you agree?
Yes, sir.
Yeah. So the presentation is on the theoretical part, right? And we again start at exactly sharp at 6, and this time we'll try and finish by 7:30 sharp. And all of you are going to speak 8 minutes and 2 minutes changeover time. And strategy has been worked out, right? Great. Just an announcement. I move on with the next topic. Now we are going to study a set of forces, which are the surface forces important for microfluidics, and a set of forces. Lecture 4 will be on the surface forces, and lecture 3 and 4 at the end of lecture 3 and 4 will be, at the end of lecture 4 and lecture 5 will be 5 and 6 perhaps, will be some of the body forces that are very, very relevant for the microfluidic devices. Okay. Now question is, what is a surface and how the different types of surface properties that emerge, right? So this I have already discussed, that if you have a fly, if you look at the eye of a fly, you will find like, this sort of artificial microscopic structures, microstructures, nanostructures that are embedded, which helps the fly to develop a kind of very, unique eye, which has got very unique property. Similarly, we also discussed about the gecko pad, where you could see that these fibrillar surfaces that gives the adhesive property, which is called a pressure sensitive adhesive, which actually gives them the capacity to climb the wall, which is a very unique property, just like to the spiders also. Okay, we have already looked at, and then this type of thing can be used for different types of applications, right? But say suppose if somebody has this fibrillar surface, and then it is attaching to the wall, and then it is getting attached. Can you tell me what is the force that is associated with that? What type of force? The attachment. So suppose, fine, take care, there is a fibrillar surface. You have a lot of different types
Is it van der
of.
Waals?
Yes, but how exactly this van der Waals force they appear?
Because it is, sir, very loosely held, sir.
What is a van der Waals force? Do you have any idea?
Yeah, interaction between two dipoles or something else, something like that, sir. Forgot exactly.
Right, but interaction between two dipoles means what? See, this is called dipolar interaction, right?
Correct, sir.
So there are a class of forces which are called very weak forces, right? Those weak forces, they come into action when you take two surfaces. Say suppose in this situation, one surface is the hand of the Spider-Man, and the other surface is the wall, right? When you bring in these two surfaces very close to each other, at the immediate vicinity to each other, what happens, like, you may see these different types of van der Waals forces they manifest, different types of surface tension forces they manifest, which is the main focus of this particular next two lectures. Okay, lecture 4, lecture 5, you will find that we are going to really discuss about how to really master the art of understanding the surface tension and the van der Waals forces. So before we really move to the nitty-gritties of that, can you tell me what is a surfactant? Anybody has any idea that what is a surfactant?
Sir, molecules which are used to mix oil and water, sir.
What type of molecule?
It can be any molecule, sir, but they help us mixing the oil in water.
What is the design of the molecule?
Surfactant molecule, sir. Sir, they contain both hydrophobic and hydrophilic part.
So suppose you have oil, right? And suppose you have water, right? Now you want to mix them. How do you mix them? What will be the molecular design that will allow you to mix these two?
So one part should be attracted to oil and other part should be attracted to water.
Right. So it has a hydrophilic. Sorry. It has a hydrophilic head. And it has a hydrophobic tail. So this is nothing but CH2, 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 CH2. So you have essentially, say suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this might be sodium dot acyl sulfate. So 12 CH2 group. So whenever you have the CH2 group is coming as the tail, so this is an organic material. So this will be what? This will be hydrophobic, right? If it is hydrophobic, means that is oleophilic. That means it will like oil and it will hate water. And hydrophilic means oleophobic. So which is like, say suppose sulfate, sulfonic acid, SO3H. Right. So a material, if you can synthesize a material which is having a kind of hydrophilic head and hydrophobic tail. So what will happen? The material will reside like this. The material will reside like this. Material will reside like this. So hydrophilic head is towards water, and hydrophobic tail is towards oil. Now this is in a very dilute situation. If you just suppose if you just keep putting more and more surfactant into it, what happens beyond a concentration which is called the critical micellar concentration, they start agglomerating in a beautiful way. Say suppose in water, say you have a water bath and you have put this surfactant, and beyond a certain concentration you will find in water it will form like this. And these are called the micelles. So what is the arrangement? You see that all hydrophobic heads are outside, which is in connection with the water. And then inside you have all the hydrophobic tails. So essentially this is the oil phase. Right? In case of oil, how will I see this same? Sorry. In case of, say, suppose if I have a beaker filled with oil, what will be the configuration of the micelle? Anybody can tell me?
So heads will be inside and the tails will be outside.
Right. So you may see that a reverse micelle formation will take place where the heads will be inside. So hydrophilic part, so they'll be inside water and outside there'll be oil. Right. So you can see that in water, say suppose inside there is this water, so it will be something like this. Whereas if outside water is there, this will be like that. So different types of micellar formations takes place, which leads to beautiful, interesting, not only chemistry but also physics associated with the surfaces. But we will see the usage of the surfactant. So what generally, Govindo said that it is used to mix oil and water. Now my question is, why should it mix oil and water? Any idea? Say when I put this into a oil water interface, why should it mix oil and water? Now, a smarter question to ask, what demixes water and oil? So suppose if I have a water bath, right? And then if I put oil on top of that, why don't they mix with each other? What is the reason? Any idea?
Density difference.
Yes, density difference, but why are they immiscible?
Because one is polar and other is non-polar in nature.
That's okay. But then why they are not mixing with each other? I mean, polar, non-polar, fine. But then physically, what is the reason why they are not mixing with each other? Now, if I ask you the question that say, suppose if I put alcohol, then why it mixes with water?
Because it can form bonds, sir.
Not only form bond, that's where the role of surface tension comes into picture. Right? That's where the role of surface tension comes into picture. So first we have to understand what is surface tension, or like, what are the different surface forces that are there at the surface. And how are they going to really influence scientifically if you put a surfactant, right? So this question we are going to come back a little later. Now, what does it do in general? Say, suppose if you have a stain, which is generally organic, and you have a water solution, which is your generally like, normal, in case of washing, you have water, you have put some surfactant. This surfactant actually binds. You can see that the hydrophobic one has binded on the oil. And moment it agglomerates like that, what happens? The surface tension of the stain reduces because you have put a surfactant. And that we will understand why the surfactant actually is reducing the surface tension. Now, moment the surface tension reduces, what happens? It helps in dislodging this particular stain from the surface, right? And then it goes out. This is a roll-up process. This is an emulsification process. So why these mushrooms are coming up? Because now, since the surface energy has reduced with the help of with the addition of the surfactant, what happens? Like then the smaller bubbles, bigger stains can be broken into smaller pieces, and they can be detached out of the surface, and that is the exact mechanism of cleaning. Now here, if you brush a little bit, you put some more energy, the entire stain or dust will be out of the surface. Right? So surfactant actually is a game. It's surfactant. With surfactant, you play a game to really maneuver the surface tension force in order to really do the different types of cleaning actions. And it has a very beautiful science behind it, which we'll try to understand. Now this, you see the lotus effect. You have a lotus leaf. On top of that, if you put a water droplet, you will find that they will not at all wet the surface. If you do a microscopic scanning electron micrograph image of this lotus surface, you will see that there'll be a hierarchical structure. These are all microscopic structures. On microscopic structures, you can see grain-like nanostructures, which are called the hierarchical structures. So essentially, on those hierarchical structures, the water droplet sits like this, right? So this is not only a kind of super hydrophobic surface where water doesn't sit, but this is also a self-cleaning surface. It will always have an inclination. So now once the water droplet rolls, what it will do, it will remove the dust particles. So it is not only super hydrophobic, but at the same time, it is also self-cleaning. These are two different applications. These are most of the flower petals, leaves, stems, they are all embedded with different types of microstructures on the surface, on a hydrophobic surface, to make sure that they just don't get first they are not hydrophilic in nature, because more water means more chances of infection, more bacterial growth, more fungal growth. Second is moment water comes, they make use of the water to make it self-cleaning, which can be a very interesting addition to our technological domain. Like say suppose when we make cloths and all, this sort of technicalities can be included if we really understand the surface properties well. Now, in order to really get into depth of what is happening here, I said that oil, water, they don't mix. Whereas in case of alcohol and water, they mix with each other very easily. What is happening here? Now, if you bring in one surface towards another surface and they are not same, say suppose one is oil and one is water, this process is called adhesion. You are trying to bring in two different surfaces towards each other. That is called an adhesion. Whereas if you bring in the same material, say suppose you are pouring water into water, that particular process is called the cohesion. Okay, adhesion means two different surfaces. Cohesion means the same surface. Now, if you bring in two different surfaces, right, and then when you join them, if they don't release the energy, then they will remain separated. So suppose if you bring in oil, if you bring in water, moment they join with each other, moment they interact with each other, if they don't release any energy, right, either through the formation of bond or through the formation of the solvation, solution and all these things, if they don't release any energy, what will happen? They will remain as is. Okay. Now, and then they're very easy to, so they are not adhering to each other. They are just physically sitting on top of each other. Correct? Now, if that is not the case, say suppose in case of alcohol is getting solvated into water. So alcohol is surrounded by water molecules and water molecules are surrounded by alcohol, which is leading to the release of some energy. Polarity, non-polarity, these are all different arguments. So two polar solvents, they should mix with each other, right? Why they mixes with each other? But because two polar solvents, when they come towards each other, one polar is solvated by the other polar molecule and there is an energy release. And that release is called the work of addition. So suppose initially you had gamma 1 and gamma 2 and at the end of the process you have gamma 1, 2. So initially you had gamma 1 and gamma 2. When you have joined them, you have only at this interface, that is gamma 1, 2. Now this particular energy, say at the end of the process, whichever direction you are going, if in this process energy is released, then also that is feasible. In this direction, if energy is released, that is also feasible. So whatever you are doing, if it leads to release of some energy, then only that is a spontaneous process. The release of the free energy, then only that is a spontaneous process. Otherwise not. Same for the work of cohesion. So if you have a surface, right? Let me put this way, that if there is a surface that is joined, suppose I have put some adhesive here in the middle. So what will happen? Say suppose I have a solid, this is like an envelope, right? The top of the envelope and bottom of the envelope, and I have put an adhesive. Now, in order to separate them, to make it gamma 1 and gamma 1, I need to do some work. Otherwise, they will not get separated. They will remain as is. Until or unless you tear this and all, it will remain as is. Why? Because the energy that you put in, that is more than the adhesive energy that is between these two. Right? Same here for the work of adhesion. Say, so in this situation, what is happening? Say, suppose you are looking from a process here to here. Initially, the energy was at this place, you had gamma 1, 2. Finally, what you have created rest of the energy, surface energies are remaining same. They will cancel out here. This will cancel out this will cancel out that, this will cancel out this will cancel out that. So all these other surfaces will cancel out. That's why they are not considered. So in this situation, when it was in a joined adhered state, the energy was gamma 1, 2. When you separated them, this has become gamma 1, this has become gamma 1. So finally you have gamma 1 plus gamma 2. Then initially you had gamma 1, 2. If you take the difference, that is your work of addition. Okay. Next, say suppose you have initially a cohesive, say you have a water column, and you have divided the water column into two. So initially there was no energy because it is same. But you created two surfaces, gamma 1 and gamma 1, just by separating these two columns. So then, your work of cohesion is 2 gamma 1. So you have to invest 2 gamma 1 of energy in order to do that. Here, you have to invest gamma 1 plus gamma 2 minus gamma 1, 2 in order to separate them to like this. So whatever energy you have to invest, that is here called work of addition. Whatever energy you invest here, that is called the work of cohesion. Okay, clear? Now let us look at the molecular perspective. What is an addition from the molecule? You know that inside the molecule, we satisfy all the coordination numbers. Okay, so these are all in some sort of structured states. In case of a solid, it is a lattice. In case of a liquid, it has a specific arrangement. So this particular area is the bulk of 1. This particular area is the bulk of 2. Whereas on the surface, you don't satisfy the full bonds. Okay, on the surface of 1 and 2, you are not fulfilling it is not possible that on the surface, that's why surface is different from the bulk, because on the surface, you are always dealing with unsatisfied bonds. And that is the origin of the surface tension force, that when you have 1 and 2 brought in together, okay, so what is the free energy of addition? Initially, they were separated, gamma 1 plus gamma 2. When you bring in towards each other, it has become gamma 1, 2. The difference between gamma 1, 2 minus gamma 1 plus gamma 2 is, if delta G is negative, then it is a spontaneous addition. If delta G is positive, then it is an addition failure. They are not going to adhere to each other. Sorry, they may stay with each other, but they will not adhere to each other. How do I calculate that? So E bulk, I can say that V11, Z1. Okay, what is V? V is the interaction potential, and Z is what? Z is the coordination number. Okay, and in the bulk of 2, that is V2, Z2. At the surface, you may see that V11, Z1 is, and these coordination numbers, you can see that they are different. One is related to 1, one is related to 2. And when I have brought into each other, you may see that V12, Z12 and V21, Z21. Now, these molecule by molecule, if I do an averaging, I will be able to really come up with the case that, in case of a situation where gamma 1, 2 is equal to N into E bulk minus E surface, where N is the number of pairs per unit area. By the way, what is gamma here? What is gamma here? What is gamma here? This gamma is called the surface energy, the excess surface energy per unit area, or the surface tension. Energy per unit area, that means joule by meter square, that means Newton meter by meter square, that means Newton per meter. Correct? Which is the surface tension, that the unit of that, what? Newton per meter, right? So here, we are dealing with whatever we are writing here, this is the surface energy, gamma 1 and gamma 2 and gamma 1, 2. So what is surface energy? Surface energy is what we are talking about here, joule per unit, joule per meter square, right? So what is joule per meter square? Newton meter per meter square, right? So that is Newton per meter, which is again, so this is the way you divide the excess surface energy, which is synonymous to what? Surface tension. Now, if this is surface tension, this is surface tension, this guy is called the interfacial tension. When I deal with surface tension, I assume that this is in vacuum. This part is also in vacuum. Whereas when I deal with interface, I say that one is in connection with two. Okay. Now, in this situation, I have created two surfaces out of a cohesive surface. So you can say that in these places, I have developed some unsatisfied bond. In this situation, I have unsatisfied bonds here, unsatisfied bonds here. They are combining something like this, right? So what is the main definition of that? In the bulk, you have different, on the surface you have different. So this is the molecular picture of a surface tension, and because of this unsatisfied bond, any material that you put in, there can be a release of energy, either through bond formation or through physical association. And whatever energy that is released because of the material that has been put, that is called the adhesive energy. If it is a different material, then it is adhesive energy. If it is the same material, that is called the cohesive energy. Okay, so this was the first experiment through which this particular property was measured. That you have done this in your childhood, that you had this generated the soap bubble, right? You took a soap solution and then you started putting some air and it had just expanded like that, right? So here what you are doing, you have taken a filament like that, and then you have put a soap film, and then you are trying to put a force here, right? So experiment on surface. Extend the liquid film of width L by a length dx. So you have extended it by a length dx. So increase of the surface area on both the sides is L star dx. You have two surfaces, right, for a film. So you have got, and then what you say that observation constant force F is necessary. It is not like a spring. Force increases with elongation x for x. So Hooke's law is F is minus k star x. Just now we have studied. Right. Now here, how do you do it? So you say that dW, that is the work done, which is the force into displacement. That is the force that you have applied. What is the force? Force, you say that, so surface tension is what? You say that sigma, okay, which is your surface tension here, into 2L, the length on both the sides into, so this is Newton per meter, okay. And then, dx is what? Dx is already there. So Newton per meter into the length, meter. So that leads to the force. Sigma into 2L is your total force, and then you have dx, right? And then you define sigma is what? dW by dA, which is dW by 2L dx, which is the area, which is F by 2L. So F by L leads to what? F by L gives you the surface tension. Newton per meter or millinewton per meter. And that is equivalent to work per unit area or energy per unit area. When you express in terms of energy, you call it surface energy. When you express in terms of force, you call it as a surface tension force. So you have different types of materials with different types of surface tension. Like the most strange material is the strangest liquid, that is available in the globe is called water. This is, by the way, this is perhaps German. So they are writing washer. This is water. Okay. So 72.75, that is millinewton per meter. In Newton per meter, this is 72.5. 0.0725 Newton per meter. Right. So this has the water has the highest. Water has a molecular weight of 18, but this is in liquid state. Why? Because it has a lot of hydrogen bonds and it has the highest surface tension. Again, because of the unsatisfied bonds that are there at the surface. It's a very, very interesting material because at that molecular weight, you will find everything is say ethanol, methanol, you find they are all volatile organics. They volatilize even a lot of heavier molecules, they are in a vapor states. But this guy is, it is in a carbon dioxide, you see it's heavier, but then they are in a gaseous state. But water is in a liquid state owing to this typical property of forming the hydrogen bond, which is the major source of life. And in case of the surface tension also, it has got a huge, leap in terms of typically, you remember this table that, when you are really dealing with the surface energies of different materials, if you have a metal, okay, this is typically about 1,000 to 10,000 Newton per meter. Okay, if you have a metal oxide, the surface tension is about 100 to 2,000 Newton per meter. If you have say suppose graphene, okay, carbon allotropes, you will find they are about 100 to 500. If you have a polymer, the surface tension is about say suppose about 10 to 100 Newton per meter. Okay, now the least, the material with least surface tension is called Teflon. Okay, which is the most hydrophobic material. It has a surface tension of say suppose about 5 Newton per meter. Right. In this, if you just compare, say suppose all the liquids like say suppose water, okay, say suppose alcohol, okay, you will find them between say suppose 20 to 100 in between them. This is a typical order of magnitude of different types of materials. Say suppose if I go for these materials also, metal, right? Metal, if I go for elastic modulus, you will find this is about 10 to the power 12 Pascal. This is the Young's modulus, E. Now, if I go for viscosity, it is nearly 0. Right? Similarly, for metal oxide, this is about 10 to the power 12 Pascal, and then viscosity is about 0. Right? So suppose if I take polymer, you will find this will be about 10 to the power 6 to 10 to the power 12 Pascal, 10 to the power 9 Pascal. And then viscosity will be of the order of say suppose 10 to the power 5 to 10 to the power 2 Pascal second. Right? Now then if you have liquids, you will find that elasticity is nearly 0. Viscosity will be of the order of say suppose minus 10 to the power 3 to about 10 to the power 2 Pascal second. So surface tension, viscosity, elastic modulus, 3 major surface properties. You can really classify. You can have an order of magnitude survey on these properties, and these actually give you a lot of information about how do you use which material to use in which place and how exactly you mix different materials to come up with a type of mixture property associated with its surface tension, with its viscosity, and with its elastic modulus. The most standard way of measurement of surface tension is called the contact angle measurement. Okay. How you perform the experiment? You perform the experiment like this. Let's say suppose you have a surface. You have a surface, and on the surface, you have put a drop which is forming a lens like this. Right? Now, when you drop a surface where the lens is formed, let me just draw a little better here because that will put me in much better situation. Yeah, sorry. So what is Young's equation? So suppose I have a surface and then I have a liquid drop like that. Okay. Now in this liquid drop, this is a solid, this is a liquid, and this is a vapor. So here in this interface, I have gamma LS. At this interface, I have gamma LV. Okay. And at this interface, I have what? Gamma SV. So I take this point, which is called this particular point. This you can from the top, you can understand that this is a kind of circle, which is called a three-phase contact line, TPCL. So in that, what I draw a force balance. So one force is in this direction, one force is acting in this direction, and the other force is acting in this direction. So these are the three different forces that are acting in this direction. What is this force? This is essentially gamma LS. What is this force? This is gamma SV. Right now, if I just do a force balance in the x direction, gamma SV is counterbalanced by what? Gamma LS plus, if I define this angle as a contact angle, which is theta, right? This is called gamma LV cos theta, which is equal to gamma SV. Right? So essentially, that is what is the Young's equation. So you just have the force that is acting. This is SG, this is SL, this is LG. LG cos theta plus SL is equal to LG cos theta plus SL is equal to SG. And then from there you get the theta. You measure this theta, and from there you experimentally measure this theta in order to get the surface tension of sigma L. If you take sigma L, you take a surface where surface properties are known, you take a liquid where SL is also known, and from there you obtain the sigma L. Right. So this is the way typically, generally people, I think the methods are there. You use this sort of contact angle goniometry through the liquid you dispense from here. This is a goniometric arrangement through which you have the image, and from the image you calculate the theta, and from the theta you obtain this. This experimentally you measure the surface tension. Now based on the contact angle, if theta is equal to 0, then that is a liquid is forming a film on a surface. That means it is a weightable surface. Okay. If it is forming a lens, then these are all incomplete. Okay. And if it is forming a kind of drop like this, that is a non-weighting surface. So in this sort of situation, this is about 108, contact angle is 180 degrees. So you can really classify from 0 to about 20-30 degree, it's a weighting surface. 20 to about 100 degree, it is about incomplete weighting surface. And beyond 30 degree, it is a super hydrophobic surface. Beyond 130 degree, it is a kind of a super hydrophobic surface. So based on the surface tension, the contact angle measurements, you can really classify different types of solid surfaces on how exactly, say in this situation, the surface is what? If this is a water droplet, the surface is super hydrophobic. Okay. In this situation, the surface is hydrophobic. In this situation, the surface is super hydrophilic in case of these droplets are water droplets. On the other hand, if these water droplets are oil droplets, this is a surface which is an oleophilic surface, right? Whereas this is a surface, this is a super oleophobic surface. So different types of materials, chemicals, you can really use for hydrophilicity, hydrophobicity, oleophobicity. The most general terminology that is used called lyophilic and lyophobic. If a surface likes to form on a surface, if you put a liquid, if that liquid is weighting the surface, that's a lyophilic surface. It can be oleophilic, it can be hydrophilic. Okay, whereas if it doesn't like the liquid and it forms lenses, then what happens? Then you call it a lyophobic surface, right? Most importantly, when you do this sort of experiments, no, when you drop the liquid, this liquid not exactly reaching the contact angle immediately. Either the droplet is spreading, then it is retracting, then it is spreading, then it is retracting before it is getting into the equilibrium contact angle. So this, when you dispense a drop, you will always find this contact line is moving, and that is what is called the contact angle motion, or contact line motion, or the contact angle dynamics. So suppose if you have a contact angle like this, if you have a situation like this, in this situation it is advancing. So when it is advancing, it will be advancing on a dry surface. Whereas when it is receding, if it recedes from this direction, it will be receding on what? It will be receding on a wet surface. So advancement and receding of a contact line is not a reversible process, and there will be a hysteresis associated with that. Why? Because advancement is always associated with a dry surface, whereas the receding of the contact angle is always associated with the wet surface. You measure contact angle like this. You also measure using a capillary rise method. What is the method here? You put a capillary into the, you take a glass capillary. Say suppose you have a water bath, you put it, and then what happens? You measure the rise. So what is the upward component of the force? You know that this is theta angle, and then 2 pi r, which is the perimeter, into gamma 2 pi r cos theta, that is acting in this direction. In order to pull this up, surface tension is acting in the vertical direction, whereas what is going in the downward direction, it is the total weight. If you balance these two from the height, you will be able to, you measure the height from there, you will be able to measure the surface tension gamma, which is to be obtained. The other method is called the Dunoyering method. What you do, this generally is used for the measurement of the interfacial tension. So you create an oil water interface like that, and you place the Dunoyering at the interface like this. And then, you connect this Dunoyering with a, it looks like this, with a pulley where you start putting the weight, right? And at a particular situation, it will start pulling the surface like this, and beyond a certain weight, it will fail, right? So that force that you calculate from the weight, and then it has 2 pi r1 in the inner contact line and 2 pi r2 in the outside contact line. So that is the total area, that total perimeter that you are covering. So force per unit length, that gives you the surface, the interfacial tension. So this is the way you measure the interfacial tension between oil and water, right? So Young Laplace, we do it in the next class. So I stop here. Any questions up to this point? Any questions?
Sir, that coordination number and potential, I didn't understand. Can you please explain me what is that coordination number?
Yeah, it will come
Sir,
back once again. Yeah, bolo.
Sir, one more thing. As you mentioned that all the coordination numbers like with the metal are not fulfilled fully. So how does it become stable there, sir?
Where?
Because on the surface.
No, it is
yes,
not
sir.
stable. It is not stable. That's
because
the reason.
It will react.
It can react. It is always reacting. Any surface is always reacting. Say suppose you have a gold ornament, right? It always gets oxidized, right?
Yes, sir.
Why is that so? If you have a steel watch, right, it always gets oxidized. So any surface is always reacting surface. But given the condition that you have to have the adequate condition, it's always trying to react. It is always trying to fulfill the coordination. Okay, am I clear?
Okay, sir. Okay, yes, sir. Thank you, sir.
Achha. So E bulk is clear, correct? E bulk you are okay with, right? So interaction, V is the interaction potential. And Z is the coordinate. So say interaction, say suppose interaction means cell jones, 1, 1, right? And then how many are there? So 1, 2, 3, 4, 5, 6. That is your V11, Z11, right? V22, Z22. Similar will happen in this Z1S is different. Here it is 1, 2, 3, 4, 5, 6, right? But here it is 1, 2, 3, 4, right? So that's why Z11S is different. Am I correct? So V11, Z1, so you have 4, and then V22, Z2, you have this, and then what happens? Then you have V12, this 1 and 2, 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 right? And then you have 2, 1, 2, 1, 2, 1, 2, 1, 2, 1. So this is that component. So this is the total surface energy when you have brought them in together. Correct?
Okay, sir.
This is in the bulk and this is in the surface. 1, 2 means what 1 is filling in presence of 2. 2, 1 means what 2 is filling in presence of 1. Right? So V11 is the potential. So this is the total energy at the surface. You know, this is only one situation I have shown. There will be so many, there will be an array of molecules here. Right? So first is what is their individual interactions? And then second is what is their, so these two are individual interactions. This is 1, 2, 3, and this is 1, 2, 3, 4. So these are the two, whereas these two are, this one is what 1 is filling in presence of 2 and what 2 is filling in presence of 1. So that is the total energy. So this is the total energy.
Sir, 1s is, sir, 1s and 2s, that is what 1 is feeling with the, I mean, between 1 and the surface.
No, this is only for, see, when you are convinced V11, Z11, right? See, when you have bulk, you have completed
Yes,
all the coordination number, right? So it is 1, 1, 1, 1. See, what is V11? Interaction potential. Z is the coordination number. This how many? You have 1. See, V11 is how many is there? For 1, it is 1, 2, 3, 4, 5, 6, right? Am I correct? In case of bulk, have you understood that? Yes. V11 is the interaction potential. I have 6 such because of the coordination number. Am I correct? Yes. Per unit lattice. Yes.
Yes.
Now for in the surface, it is not the case that I have 6. In the surface, for this I have 4, for this I have 3. That is Z11S. That is Z22S.
Okay, sir. Understood.
Okay. And then I have 1, 2. This also is coming in addition. So now what will be gamma 1, 2? If you take the difference between these two, so number of pairs per unit area. Right. So this is the additional thing that is coming because see, suppose if these two surfaces are separated, these two are not at all there. This is only the surface. When I brought these two in towards each other, what happens? So what is gamma 1, 2? Gamma 1, 2 is N is the number of pairs per unit area. E bulk minus E surface. E surface, why it is originating? Why these terms are originating? Because they have now come close to each other to satisfy a part of the bonds here.
Okay, sir.
Understood? Yeah, more discussion will happen.
Yes, sir.
As we progress. Whenever sports comes, it will be more clear. Fine. Take care. Any other question? No? Take care. Thank you. So we meet on Friday at 6 p.m. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.